All right, welcome. So today we will talk about electric potential and electric potential energy. All right. So just as a heads up, these topics here today that we'll be discussing are not covered on the AP Physics 1 exam. That being said, I do think learning about these topics is important as to give us a little heads up and an understanding of why things happen when we're dealing with circuits, which is what we'll talk about next lesson. So kind of our goal here is we're going to want to learn how basic DC, meaning direct current circuits work, right? That's what is expected from the AP exam, all right? So today we'll learn a couple things and how kind of the behind of why circuits work, the physics behind it. And then kind of we'll focus on with circuits, just kind of the mechanics of solving those circuit type problems. Now, what's really useful and important about circuits is that it allows us to kind of control the energy transfer from one spot to another, right, in a very kind of organized way, and we can use electrical energy to do things we want, like power a light bulb, or, well, in real life we use circuits for a lot more complex things than that, but that would be a simple situation. So, talking about electric potential energy, so again, potential energy, we use the symbol capital U. So we use a little subscript E there for electric potential energy. So this is the potential energy associated with electricity, right? So you guys know if you attach a battery to a light bulb properly, you cause a light bulb to light up, right? And there therefore is some sort of energy stored in that battery, and this is electrical energy. All right. So another way we can kind of see the evidence of there being electric potential energy. So let's suppose, looking at this image here on the bottom left. All right. So we've got this giant sphere of positive charge. So some sort of sphere that has excess positive charge here. And then we have that dot there to the right with the arrow on it. Right. So that dot there represents a test charge that's experiencing the electric field created by these source charges, right? So we'll assume that charge is positive, all right? So we have two positive charges some distance apart away from each other. So therefore they exert forces on each other, right? And since they're both positive, they're a repulsive force. So that arrow there represented on that point charge is rightward because it's being repelled from the source charge. Granted, we should be also drawing an equal arrow in opposite direction on the source charge, but I digress. This is the image that I found. But looking at this source charge, assuming that it was at first stationary and it's at that location there, right? If we were to then allow it to move, if the only force acting on it is that electric force, well then there is a net force acting on the object and therefore it's going to accelerate. So it'll go from not moving to moving. So we know it then has to gain kinetic energy. So that energy has to come from somewhere. And that's what this electric potential energy is. So there is some sort of energy here just by the fact that these charges are interacting with each other. That being said, another interesting thing is, well, if we had this test charge be closer to the source charge, well, then it would feel a larger force and therefore gain more kinetic energy. So we would know that then there has to be more potential energy when that test charge is closer to that source charge. Something we'll look at in a little bit later. But I'm going to make the corollary here of comparing gravitational potential energy to electric potential energy. All right, so the way gravitational potential energy works is that we have there's going to be a change in what that gravitational potential energy is depending on the location of the mass, with respect to the gravitational field, right? So kind of very simply speaking, right, we know the force of gravity we can write as mgh, assuming that we're dealing with a uniform gravitational field. So the larger h is, right, the more gravitational potential energy there is. So that's because that mass is moving in that gravitational field. Now, another thing we know about the gravitational force is that it is conservative, Right? That means that the work done by the gravitational force only depends on the start and end point, not the path. All right? We also know the formula being gmm over r squared. For electric potential energy, well, we have very similar things going on. So electric potential energy is going to change on whether or how the charge is moving in the electric field. And an electric force is also conservative. All right, so and the force again looks very similar. So therefore, I'm going to make the argument that since the potential energy due to gravity has the form of negative gmm over r, the electric potential energy will also have this form. And this is actually due to the fact that we're dealing with conservative forces. So electric potential energy, we can compute this by taking K, being the Coulomb constant, multiplied by the two charges interacting with each other divided by r. And when you plug in the charge here, you do want to include the positive and negative sign. And the reasoning for that is you notice that kind of the difference between these two formulas is the negative sign. So a negative sign here means attractive. What the force that's causing this potential energy is attractive. So if you look at the diagram below, the plot for A, the gravitational potential energy, this is always below the zero horizontal axis here, because gravitational potential energy is always technically speaking is dealing with negative, meaning attractive. So masses, when you're dealing with mass, they always attract to each other. There's no such thing as mass repelling, interestingly enough. So mass is always attractive, so we have that negative sign. So similarly, if we were looking at a situation where we have a positive charge and a negative charge, so this is situation B here, then our formula would end up with a negative sign because one charge is positive, one's negative, giving us a negative value. So our potential energy graphs look very similar, and we're dealing again with charges here that are attractive. But dissimilarly, is that a word? We'll go with it. If we had two charges that had either both positive or both negative, so same attribute, I guess we'll call it, then our potential energy is going to be positive, meaning we're not dealing with an attractive force here. All right, so that's where we do have a difference compared to gravitational potential energy. All right. So again, since we're dealing with potential energy, remember potential energy only manifests if we're dealing with a system, if we're dealing with our force being internal to our system. So if we include both charges that are interacting to be inside of our system, then that electric force is internal, therefore we have electric potential energy. All right. We could also define our system just to be one charge. Right, so therefore the electric force will be internal, and instead of electric potential energy, we have the work done by the electric force instead. All right, kind of the logistics of that is kind of complicated to compute, so I do recommend including both charges in your system and using electric potential energy. It's a lot simpler. So a lot of talk, and where does this lead to us? This leads us to talk about something called electric potential, right? And this is very important because, well, this will be associated with batteries and the voltage of the battery, all right? So electric potential, we use the symbol capital V to represent it, in part because we're dealing with voltage. So electric potential and electric potential difference. And electric potential difference, spoilers, that is voltage when you're talking about a voltage of a battery. Okay, so electric potential is an expression that allows us to represent the amount of electric potential energy available per unit charge. All right, so this means that if our charge is in one spot, the electric potential at that spot is an expression of how much energy is available for that charge. All right, it's a scalar quantity, and it decreases in the direction of the electric field. That part's not so important, but basically just note that it allows you to know how much energy is available for that charge. So electric potential difference will just be the difference in this quantity between two different locations. All right. So in terms of the computation, right, we could look at this formula below, that the difference in electric potential energy is your change in electric energy available for whatever charges you're looking at. In terms of units, we're dealing with, well, our numerator is energy, so that's joules, and our denominator is charge, that's coulombs, giving us a joule per coulomb, which is defined to be a volt. So electric potential and electric potential difference have units of volts. So it's going to be very useful to look at an example here, and I have a recording of this in a different video, so please take a look at that. So finally, when we're dealing with objects, charged objects, they're going to tend to accelerate from one point to another, right? And if they do that, that means there has to be an electric potential difference between those 2 points. If it's accelerating from one point to another, that means that there is an electric force that's pushing this charge. Just kind of FYI, when we're dealing with positive charges, they get accelerated from a high potential to a low potential. That'll be useful when we're thinking about batteries and circuits. And also, confusingly enough, it's also useful to think about negative charges moving from a low to high potential. All right. If you want to learn more about kind of the nitty-gritty and the details of this and learn about this more in detail, taking AP Physics C or AP Physics 2, we do talk about these in more detail. So it's kind of a long story short in terms of this lesson, and a lot of kind of strange new vocabulary. But finally, I do want to mention, if there's no change in potential difference, right, so there would be no force to accelerate charges. So this would be kind of the equivalent in terms of a circuit, which we'll talk about again later, if you had a battery with no charge to it, right? You have a dead battery, I should really say. If you have a dead battery, that means that the electric potential difference of that battery is 0, and that's pretty useless, and which would mean that we can't accelerate charges, and means we can't give them any energy, any kinetic energy, I should say, in doing any work. All right. So that's what I have for you for this lesson. Again, this lesson here was not going to be examined on the AP exam, but then next class, or next lesson, when we talk about circuits, this is our background to talking about why circuits work. All right. Thank you.